So right over here, I've graphed the function y is equal to f of x. I've graphed it over this interval. Looks like it's between 0 and some positive value. And I want to think about the maximum and minimum points on this. So we've already talked a little bit about absolute maximum and absolute minimum points on an interval, and those are pretty obvious. We hit a maximum point right over here, right at the beginning of our interval. It looks like when x is equal to 0, this is the absolute maximum point for the interval, and the absolute minimum point for the interval happens at the other endpoint. So if this is a, this is b, the absolute minimum point is f of b, and the absolute maximum point is f of a, and it looks like a is equal to 0. But you're probably thinking, hey, there are other kind of interesting points right over here. This point right over here, it isn't the largest. We're not taking on this value right over here. It is definitely not the largest value. Is definitely not the largest value that the function takes on in that interval. But relative to the other values around it, it seems like a little bit of a hill. It's larger than the other ones. Locally, it looks like a little bit of a maximum. And so that's why this value right over here would be called, this value right over here, let's call this, let's say this right over here is c. This is c, so this is f of c. We would call f of c is a relative maximum value. Relative maximum value. And we're saying relative because it's obviously the function takes on other values that are larger than it. But for the x values near c, f of c is larger than all of those. Similarly, I can never say that word. Similarly, if this point right over here is d, f of d looks like a relative, f of d is a relative minimum point, or relative minimum value. F of d is a relative minimum, or a local minimum value. Once again, there's over the whole interval, there's definitely points that are lower, and we hit an absolute minimum for the interval at x is equal to b. But this is a relative minimum, or a local minimum, because it's lower than if we look at the x values around d, the function at those values is higher than when we get to d. So let's think about, it's fine for me to say, well, you're at a relative maximum if you hit a larger value of your function than any of the surrounding values, and you're at a minimum if you're at a smaller value than any of the surrounding areas. But how could we write that mathematically? So here I'll just give you the definition that really is just a more formal way of saying what we just said. So we say that f of c is a relative maximum value if f of c is greater than or equal to f of x for all x that we could just say kind of in a casual way for all x near c. So we could write it like that, but that's not too rigorous because what does it mean to be near c? And so a more rigorous way of saying it, for all x that's within an open interval, of c minus h to c plus h, where h is some value greater than 0. So does that make sense? Well, let's look at it. So let's construct an open interval. So it looks like for all of the x values and you just have to find one open interval. There might be many open intervals where this is true. But if we construct an open interval that looks something like that. So this value right over here is c plus h. That value right over here is c minus h. And you see that over that interval, the function at c, f of c, is definitely greater than or equal to the value of the function over any other part of that open interval. And so you could imagine, I encourage you to pause the video and you could write out what the more formal definition of a relative minimum point would be. Well, we would just write, let's take d as our relative minimum. We can say that f of d is a relative minimum point if f of d is less than or equal to f of x for all x in an interval, in an open interval, between d minus h and d plus h for h is greater than 0. So you can find an interval here. So let's say this is d plus h, this is d minus h. the function over that interval, f of d is always less than or equal to any of the other values. The f is of all of these other x's in that interval, and that's why we say that it's a relative minimum point. So in everyday language, relative max, if you're larger than if the function takes on a larger value at c than for the x values around c, and your relative minimum value if the function takes on a lower value at d than for the x values near d. In the last video, we saw that if a function takes on a minimum or maximum value, min-max value for our function at x equals a, then a is a critical point. Then x equals a is a critical point. But then we saw that the other way around isn't necessarily true. X equal a being a critical point does not necessarily mean that the function takes on a minimum or maximum value at that point. So what we're going to try to do in this video is try to come up with some criteria, especially involving the derivative of the function around x equals a, to figure out if it is a minimum or a maximum point. So let's look at what we saw in the last video. We saw that this point right over here is where the function takes on a maximum value. So this critical point in particular was x naught. What made it a critical point was that the derivative is 0. You have a critical point where either the derivative is 0 or the derivative is undefined. So this is a critical point. And let's explore what the derivative is doing as we approach that point. So in order for this to be a maximum point, the function is increasing as we approach it. The function is increasing is another way of saying that the slope is positive. The slope is changing, but it stays positive the whole time, which means that the function is increasing. And the slope being positive is another way of saying that the derivative is greater than 0 as we approach that point. Now what happens as we pass that point? Right at that point, the slope is 0, but then as we pass that point, what has to happen in order for that to be a maximum point? Well, the value of the function has to go down. If the value of the function is going down, that means the slope is negative. And that's another way of saying that the derivative is negative. So that seems like a pretty good criteria for identifying whether a critical point is a maximum point. So let's say that we have critical point A. We are at a maximum point. We are at a max if f prime of x switches signs from positive to negative as we cross x equals a. That's exactly what happened right over here. Let's make sure it happened at our other maximum point right over here. So right over here, as we approach that point, the function is increasing. The function increasing means that the slope is positive. It's a different positive slope. The slope is changing. It's actually getting more and more steep, or more and more positive, but it is definitely positive. So it definitely meets, so it's positive going into that point, and then it becomes negative after we cross that point. The slope was undefined right at the point, but it did switch signs from positive to negative as we crossed that critical point. So these both meet our criteria for being a maximum point. So far, our criteria seems pretty good. Now let's make sure that somehow this point right over here, which we identified in the last video as a critical point, let's make, and I think we call this, let's see, this was x0, this was x1, this was x2, this was x1, this was x2, so this is x3. Let's make sure that this doesn't somehow meet the criteria, because we see visually that this is not a maximum point. So as we approach this, our slope is negative. And then as we cross it, our slope is still negative. We're still decreasing. So we haven't switched signs. So this does not meet our criteria, which is good. Now let's come up with a criteria for a minimum point. And I think you could see where this is likely to go. Well, we identified in the last video that this right over here is a minimum point. We can see that. It's a local minimum just by looking at it. And what's the slope doing as we approach it? So the function is decreasing. The slope is negative as we approach it. F prime of x is less than 0 as we approach that point. And then right after we cross it, this wouldn't be a minimum point if the function were to keep decreasing somehow. The function needs to increase now. So let me do that same green. So right after that, the function starts increasing again. F prime of x is greater than 0. So this seems like pretty good criteria for a minimum point. F prime of x switches signs from negative to positive as we cross A. If we have some critical point A, we have the function takes on a minimum value at A if the derivative of our function switches signs from negative to positive as we cross A, from negative to positive. Now, once again, this point right over here, this critical point, x sub 3, does not meet that criteria. We go from negative and to 0 right at that point, then go to negative again. So this is not a minimum or a maximum point. So we have g of x being equal to x to the fourth minus x to the fifth. And what we want to do, without having to graph g, we want to figure out at what x values does g have a relative maximum. And just to remind us what's going on at a relative maximum, so let me draw a hypothetical function right over here. So a relative maximum is going to happen, so you can visually inspect this. Okay, that looks like a relative maximum. It's kind of top of a mountain or top of a hill. These all look like relative maxima. And what's in common? Well, the graph, the function, is going from increasing to decreasing at each of those points. It's going from increasing to decreasing to decreasing at either of the points. Or you could say that the first derivative is going from positive to negative. So if you look at this interval right over here, g prime is greater than 0. And then over the next interval, when you're decreasing, g prime would be less than 0. So what we really need to think about is when does g prime, so let me see, relative, we care about relative maximum point. And so that's essentially asking, when does g prime go from positive to negative? I wrote from g prime greater than 0 to g prime less than 0. And the values that we could look at, or the points, are our critical points. And critical points are where g prime is either 0 or it is undefined. So let's think about it. Where is g prime of x equal to 0? G prime of x is equal to 0 when, let's just take g prime of x. You leverage the power rule right here. 4x to the third power, 4x to the third minus 5x to the fourth minus 5x to the fourth is equal to 0. Let's see, we can factor out an x to the third. So we have x to the third times 4 minus 5x is equal to 0. So this is going to happen when x is equal to 0. That I could, let me not skip steps. So this is going to happen when x to the third is equal to 0, or 4 minus 5x is equal to 0. For x to the third equaling 0, well, that's only going to happen when x is equal to 0. And 4 minus 5x equaling 0, we'll add 5x to both sides. You get 4 is equal to 5x. Divide both sides by 5. You get 4/5 is equal to x. So here, these are the two places where our derivative is equal to 0. Now, are there any places where our derivative is undefined? Well, our function right over here is just a straight up polynomial. Our derivative is another polynomial. It is defined for all real numbers. So these are our critical points, or we could even say critical values. Now let's think about what g prime is doing on either side of these critical values. And I'll draw a little number line here to help us visualize this. And so there we go, a little bit of a number line. And let's see, we care about 0 and we care about 4/5. So let's say this is -1, this is 0, this is 1. And so we have one critical point at, let me do this in magenta. We have one critical point here at x equals 0. And then we have another critical point. I will do this at x equals 4/5. So 4/5 is right around there. So that is 4/5. And let's just think about what g prime is doing in these intervals. And these critical points are the only places where G prime might switch signs. So let's first think about this. Let me pick some colors I haven't used yet. So let's think about the interval from negative infinity to 0. So this is the open interval from negative infinity to 0. And we could just plug in a value. Let's try negative 1. Negative 1 is pretty straightforward to evaluate. So let's see, you have 4. You're going to have 4 times negative 1 to the third power. So that's going to be 4 times negative 1 minus 5 times negative 1 to the fourth power. So that's just going to be 1. So let's see, this is going to be negative 4 minus 5, which is negative 9. So right over here, G prime is equal to negative 9. And so we know over this whole interval, since it's to the left of this critical point, we know that G prime of x is less than 0. And so our function itself is decreasing over this interval. And so we know we need to go from increasing to decreasing. So you can already say, well, we can't go from increasing to decreasing at this critical point because we're already decreasing to the left of it. But anyway, let's just think about what's happening in the other intervals. So in the interval between 0 and 4/5, so that interval right over there, so it's between 0 and 4/5. Well, let's just sample a number there. Let's say the number, I don't know, 1/2 might be really straightforward. So we can evaluate G prime of 1/2. G prime of 1/2 is equal to 4 times 1/2 to the third power. 1/2 to the third power is 1/8. So it's 4/8, or it's just 1/2 minus 5 times 1/2 to the fourth. So that's 5/16 minus 5/16. And so this is equal to 8/16 minus 5/16, which is equal to 3/16. But the important thing is it's equal to a positive value. So in this blue interval right over there, and actually let me put 4/5 in a different color so we see that it's not part of that interval. So in this light blue interval right here between 0 and 4/5, G prime of x is greater than 0. So we know our function is increasing. And so let's see what's happening to the right of this. And the easiest value to try out would just be 1. So let's try out x equals 1. It's in that interval. So when x equals 1, I'll just write G prime of 1 is equal to 4 minus 5. 4 minus 5, which is equal to negative 1. So G prime of x is less than 0. G prime of x is less than 0. So our function, so we could say G is increasing here. It is decreasing. Oh, sorry, let me be careful. G is decreasing here. The function itself is decreasing because our derivative is negative. Then our function is increasing here because our derivative is positive. And then our function is decreasing here. So at what critical point are we going from increasing to decreasing? Well, we're doing that at x equals 4/5. So we have a relative maximum at x equals 4/5. If they said, well, where do we have a relative minimum point? Well, that's going to happen at x equals 0. We're going from decreasing to increasing. But we've answered their question of where do we find a relative maximum point.